Hey everybody, someone requested that we do some answers to 8 and 9 from the last homework, so let's give it a try. The product of an even or odd function and an even or odd function is even, odd, or neither. So there's a lot of options here. I said you can choose the specific version you want to prove, and some of them are easier than others. Let's see what there is to see. So we could try and show that an even function times an even function is, well, what do we think it is? Let's do an easy example. X squared times x to the fourth. That's two different even functions that are familiar to us. If we multiply them, we get x to the sixth, which is another even function. So this suggests maybe even function times even function is even function. Let's see if we can prove it. So we'll say let f and g be even functions. Let's define h to be the product of f and g. And our question is h an even function? So h is an even function if h of x equals, h of the opposite of x, because that's the definition of being an even function. I wrote the question mark here, that's a question mark, because we're trying to figure out, is this true? That's the thing we're trying to prove. So let's go ahead and substitute what h of x actually equals. So on the left-hand side, we've got f times g. And then on the right-hand side, let's evaluate h at the opposite of x. So again, just plugging in negative x to the h function, that would give us f opposite x times g opposite x. Are these two sides the same? Well, we don't know a whole lot about f and g, except that they're both even functions. So remember, since f is even, that means f of x equals f of the opposite of x. And because g is even, g of x equals g of the opposite of x. So what that means is I can rewrite f opposite x as f of x, because I know they're the same thing because f is even. Same thing for g, I can rewrite it. So now I have actually shown that both sides are the same. And so what that means is I can choose any example even functions I want. As long as f and g are any even functions at all, I know the algebra will work out so that the resulting product is still even. Okay, cool. So that's one. What about two odd functions? Is an odd function times an odd function an odd function? Well, let's do an example. X, that's an odd function, x to the first power. X cubed, that's another odd function. If I multiply those together, that gives me x to the fourth, which is even. So one little example has suggested to me that odd times odd maybe gives me even. So let's investigate that. Okay, so same setup. F and g are odd functions this time. Let's have h be the product of the two odd functions. And I want to know, is that product of the two odd functions even? And so if the product of the odd functions is even, then h will have this relationship, because that's what it means to be even. Okay, so let's, again, plug things in. So h of x is just f times g. H opposite of x is f opposite x times g opposite x. Except now f and g are odd functions. So what that means is that this is true. Opposite f equals f opposite x. Same thing for g. That's what defines odd functions. Okay, so now I know f of the opposite of x can be rewritten this way. So here, this just becomes negative f of x. And then g, same thing. G of the opposite of x becomes opposite g of x. And now the two negative signs cancel each other out. So negative times negative is positive. So that gives me f times g, which is just what I have on the left-hand side. So that has shown me that, in general, any two odd functions, when you multiply them together, will be even. What about reciprocals? So let's say we've got an even function. Is it true that the reciprocal of the even function is also even? So this is the reciprocal. Hopefully, intuitively, this feels true to you. If you don't have an intuition about it, you can try graphing a couple. So x squared looks like this, and 1 over x squared looks like this. And this is an even function. And so if you graph a couple more examples, it should start feeling true. Could we prove that it was true in general? Well, let's do it. So let f be an even function. Let h be the reciprocal of f. We want to know, is h also even if f is even? So is h equal to h negative x, because that's the definition of being even. So let's substitute. We've got 1 over f. Is that equal to 1 over f negative x? Remember, because f of x is even, that means fx equals f opposite x. So we can just immediately rewrite the right-hand side, and we've got the identity. We've got, yep, those two are the same. So that one was pretty quick. The reciprocal of an even function, always even. Okay, what about number 9? Number 9 says, well, let's look at it. Number 9 says, prove or disprove. Every polynomial can be decomposed into two other polynomials, a and b, such that the original one is a plus b, and a is even and b is odd. So this one, you might have to read it a couple of times to understand what is it even saying. And then you might need to fiddle around with a couple of examples. So let's think of some polynomials. So if I have like 3x squared plus 2x plus 1, for example, it's a polynomial. So the question is, can I decompose this? Can I separate this into an a of x plus a b of x, so that these two are also polynomials and they add together to be that one, but one is even and one is odd? Well, there are a lot of different ways that I could have two polynomials that add to be that one. Like I could separate it out this way. I could say, let a be 2x squareds and then 1x and then 1. That'll be a. And then let's have b of x be the last x squared. And then, actually, let's make this one be 3x's, and then we'll have a negative x, and then we'll have nothing else. Okay, so you can see that when I've got an a, here's b. If I add these two together, I get my 3x squared. If I add these two together, I get my 2x squared. If I add 1 and then, the plus 0 over here, I get 1. But obviously, this is just one way of dividing it up. I could have divided it up in lots and lots of other ways, an infinite number of other ways, in fact. But let's not feel overwhelmed by the fact that there's an infinite number of ways to, sum up two things to become a third thing. Let's think about the other condition. We know that one of these has to be an even function and one of these has to be an odd function. So right away I can tell that this is not an odd function. I mean, if we were going to graph these, my guess is that this is neither and this is neither. So most of the ways that you're going to have of dividing something up, probably they're going to be neither even nor odd. So what we need to do is we need to look at simpler examples. We need some way of trying to figure out, is there a clever way of dividing them up? I think the insight comes from earlier in the problem set. Earlier in the problem set, or maybe earlier in one of the videos, you learned that an even function plus an even function is always even, and an odd function times an odd plus an odd function is always odd. And you know a bunch of examples of even functions: x squared, x to the fourth, x to the sixth. You know a bunch of examples of odd functions: x, x cubed, x to the fifth. So this actually suggests a nice way of decomposing your polynomial. Let's do the same example we had before: 3x squared plus 2x plus 1. So here's what I'm noticing. I'm noticing that this term is even and this term is odd. Is this term even or odd? Well, we'll think about that in a second. So we can already separate this into a and b. Let's say this is a of x and this is b of x. Would 3x squared still be even if I added 1 to it? Seems like the answer is yeah, because if I have a parabola and I shift it up by 1, it's still got that symmetry. It's still got that reflectional symmetry, which means it's still even. So this is still an even function. That could be our a of x. And then this is our odd function. That could be our b of x. So here I see a of x plus b of x gives me my original, and one of them is even and one of them is odd. And the way that I did it was I just grouped terms. I just said, let's take all of the terms from the polynomial that have an even exponent. I know that all of those are even functions. Let's just add all those together to be my even polynomial. Let's take all the ones that have odd exponents. Those are all my odd terms. Let's make those be my odd polynomial. And hopefully you can see that sort of in general, that's going to work. If I have like ax to the 11th plus bx10 plus cx9, all the way down to x px plus q. Again, I can just group together all of the odd terms and all of the even terms, and that should let me separate all of my terms into two separate polynomials, one with all the even terms, one with all the odd terms. Because even plus even is even, this should be an even function. Odd plus odd is odd, so that should be an odd function, and I've done it. This is all rather informal, but that's the gist of what we were getting at with that problem.